Continuing with inverse trig graphs, we want to start with y equals cosine x and find the graph of its inverse. The first thing is to figure out the domain. So let's actually just graph this guy. We know what the graph of that looks like. Now here we can't use minus pi over 2 to pi over 2, which would be from here to here, this part of this function, because it doesn't pass the horizontal line test. It's not one-to-one. It's not invertible. We'd get two possible angles for the same output, the same cosine. So we have to pick something else. Well, we still want the whole, as much of the function as possible. We want to recreate the entire output of this function from minus 1 to 1. And so we need everything from a max to a min. Well, we could do it over here, or we could do it way over here, we could do it way over here. But the simplest thing is just to start at 0 and then go up to pi. Okay, so we're going to use the domain 0 to pi. And so let me just modify that by just taking it from 0 to about 3.142. And there's our function. There's cosine. I haven't inverted it yet. I've just amputated the stuff that shouldn't be there. So here's the cosine function, the restricted guy. And now we're just going to look at the verbal description. Okay. So forward version of cosine. It starts at, let's look at an explicit point, 0, 1, and it's horizontal. Then goes down and right, getting steeper, to another easy landmark point is pi over 2, 0. And then less steep to horizontal, ending at pi, minus 1. That's what the graph looks like. Okay, so inverse cosine, we can just translate that. Inverse cosine is going to starts at, 1, 0. We just flip those two. And it's going to start out vertical like the inverse sine did. That's interesting. Okay. Then goes, down and right. That means the y is getting less, y is getting smaller, and the x is getting bigger. Okay, so now it's going to be the y is getting bigger and the x is getting smaller. Okay, up and left. That's going to be interesting. We don't usually graph from right to left, but this is basically telling us that. Actually, let me go left and up is really the literal translation. Down means y getting smaller, and that flips to x getting smaller. That's left. Right means x getting bigger. Now that turns into y getting bigger. Left and up. So we're going to graph this going left and up from 1, 0. That's going to be interesting. And then getting less steep, but note not horizontal, to 0, pi over 2. And then back to more steep, to a vertical ending at minus 1, pi. Okay, so again, I don't have it set up to do freehand, but if you just put your dot at 1, 0, then start out going vertical, then go left and up, getting less steep to this point, and then more steep to a vertical ending at this guy. What does that do? Well, I suggest you try it, but let's go ahead and actually see what the computer says is the answer, and see if that confirms what I've said in terms of the verbal description. And then we can compare the two, put them together, and see if they look like reflections of each other. Okay, so you start at 1, 0. You start out going vertical, but then immediately you go left and up, getting less steep, 0, pi over 2, and then you go back to being more steep, and you end up vertical at minus 1, pi. Okay, and let's add in cosine x, but we're going to just do 0 to 3.142. And then remember, we wanted equal scaling so we could see the reflection better. Okay, that's pretty funky. But if you look at it diagonally, if you look at the line y equals x, maybe I'll put that in as well. Let's just put in one more, y equals x, and I'll put it in dotted or dashed to show that reflect. Yeah. So here's this cosine, this piece of cosine, and you flip it around and it becomes this piece of inverse cosine. If you look at it if you tilt your head and have this look like it's vertical when you tilt your head, it really does look symmetric. But this is one of those ones that's really hard, I think. If somebody just said, given this little bit of curve, flip it real quick around this diagonal axis and get a good answer. And that's why I really emphasize this kind of thing. Specific points plotted and specific features in this sort of verbal description of how to do it gets you a good idea of what's really going on with this thing. Okay. And then the last one is y equals tan x. And so we're going to want to turn that into the inverse tan of x. Okay. So the domain, the nice thing is that there aren't three separate domains here. Okay. Well, it turns out that this one, this one shares its domain with one of the others. You can guess, if you don't want to get the answer already, you can try and guess which one. Is it the same as the sine or the cosine? Here, if we want to get just one branch of this guy and not have it fail the horizontal line test, we can again go minus pi over 2 to pi over 2. And so that's going to be, we're going to take this much. And there's the, it's kind of exaggerated now. It's not very steep right here. So here's the one piece of the tangent function. So this is the same as the restricted sine. And so, well, it's almost the same. It doesn't include pi over 2. The restricted sine function, it makes sense to plug in minus pi over 2 or pi over 2. So it was a square bracket. To be technically correct, this guy is a round bracket because you can't put in these values. It goes off to infinity there. Okay. So that's going to be the possible outputs of the inverse tan function. And what's going on with the inverse tan function is it's going to start with, ooh, that's interesting. This guy starts with a vertical asymptote. And so I'm going to start with a horizontal asymptote now. So this is inverse tan. I'm going to go ahead and skip all the way to inverse tan here. Y equals inverse tan x. Start with a horizontal asymptote at, well, where is it? What should we draw? Oh, this really, I wish that it would automatically draw it for us, but here at x equals minus pi over 2, there is a vertical asymptote. So that's going to turn into a horizontal asymptote at y equals minus pi over 2. Remember the translation. Anything to do with x turns into y. Vertical turns into horizontal. Okay, then let's see, what does this do? This goes up and to the right, and so that's going to translate into right and up. And getting, let's see, this is getting less steep, so go more steep through the origin. Then keep going and get less steep. This guy's getting more and more towards vertical, more steep, so ours is going to get less steep to another horizontal asymptote at, instead of x equals pi over 2, over here it's going to be y equals pi over 2. Okay, so let's graph that. Let's see if that makes sense with the graph it's going to give us. And here it is. Start with a horizontal asymptote at y equals minus pi over 2, through the origin, up and to the right, continually getting more steep through the origin, then less steep after, and a horizontal asymptote at y equals pi over 2. And so there's the inverse tangent function. Okay. These are, again, I'll save time by not putting these together. But if you do put them together, it's a little hard to see at first how they really are reflections of each other, but they really are. But this method really helps you kind of graph that and figure that out. Okay, so those are what the graphs look like, and we'll talk about other aspects in other videos.